Welcome to TigerGraph Fundamentals, or TigerGraph 101 certification course. We have designed this certification course for graph newcomers. We have divided the course into 4 modules, with key questions for each of these modules incorporated into the certification test online. As we go through the modules, we will review the key questions at the end of each module, so you're prepared for the online test. We recommend going through the recording for all 4 modules before taking the online certification test. Let's take a look at the 4 modules for this course. The course will introduce you to the fundamentals of graph database and analytics as a part of the first module. The second module will help you understand how graph databases compare with relational as well as NoSQL databases in terms of managing and analyzing the relationships. The third module is focused on the 3 generations of graph databases, while the fourth module gets into the 7 key capabilities for data science delivered by the 3rd generation or native parallel graph. We have included learning objectives for each module as well as multiple recap charts to facilitate your journey into the world of graph databases. As always, we welcome all feedback, and you can reach us at tigergraph.com to provide your feedback. Our first module for TigerGraph Fundamentals introduces the concept of graph database as well as analytics. It is designed specifically for folks who have exposure to relational or NoSQL databases but have not yet delved into the world of graph databases. This module also serves as a quick refresher if you have looked into graph databases some time back and are wondering what's new in terms of use cases for graph databases and analytics. There are 4 key learning objectives for this module. We want to understand the structural elements of a graph database, learn where the graph databases are used every day. We want to review key use cases for graph databases and analytics. And finally, we will look at a question that comes up very often: how labeled property graphs are different from RDF or resource description framework graphs. First, let's make sure we all know what we mean by a graph. A graph, when talking about databases and analytics, is an interconnected set of data objects called vertices, or sometimes referred to as nodes. For the sake of today's training, we will use the term vertex for each data object and vertices for multiple data objects, thus avoiding any confusion about hardware or machine nodes. The connections between a data object are called edges, and edges are data too. There are 2 types of data: vertices like a product, a customer, or a salesperson, and edges like owns, loves, is friends with, or bought. The figure here is a property graph because each vertex or edge can have properties such as age, location, or date. Graph databases represent data in the same way as we think about the world, as interconnected data objects or entities with relationships among those entities. On the left-hand side of the chart, we can see data objects such as user profile, browsing history, locations, events, purchases, and other types of transactions. These are linked together in a graph, and the relationships are analyzed for driving multiple use cases. Graph-based analytics is used for producing targeted recommendations for new products and services to recommend to a customer. It is used for predicting supply chain outcomes, specifically shortages and excess of specific parts or finished goods, and it is also used extensively for cybersecurity to understand where specific patterns of behavior among users, machines, IP addresses, and other network elements indicate a possible attack from inside or outside the organization. With that context, let's dig deeper into the structure of a graph database next. We'll get into what a graph schema and graph data look like after this, so let's take a look at the formal definition of a graph from Gartner Research, the analyst firm. Gartner published a press release in February 2019 to define graph analytics, explain the unique value proposition of a graph database and analysis versus relational and other databases, and finally forecast the growth for graph-based analytics for the next 4 years from 2019 to 2022. Gartner defined graph analytics as a technology that allows for deep exploration of complex interrelationships among various entities, organizations, people, transactions, pretty much any data that can be modeled and queried. Gartner estimates that the graph database and analytics market will grow by 100% annually through 2022, making it one of the fastest growing markets in data and analytics. According to Gartner, graph analytics will grow in the next few years due to the need to ask complex questions across complex data, which is not always practical or even possible at scale using SQL queries. Let's take a look at a specific example into the schema of a graph database. This is a healthcare example. This figure shows a graph schema where we show one of each type of vertex and one of each type of edge. A schema shows all the possible entities and relationships. The first vertex we see is the specialty of a doctor, such as cardiac care or general practice. There is a subspecialty such as interventional cardiology, which is essentially a cardiac surgeon or someone who performs operations on your heart. As we build this graph out, each of these entities or objects, specialty, subspecialty, as well as prescriber, which can be a doctor or prescribing nurse, a claim, and a patient, are all represented by a vertex, and the relationships among them is modeled by an edge. As you can see, the edges represent relationships among two different entities, such as a subspecialty and a prescriber, or a referral relationship among prescribers where they refer patients to each other. Each vertex, as well as an edge, can have attributes or fields. In this example, we can see the claim vertex has 4 fields, excluding its ID. RX field date, which is the date of the claim, the description of the claim, an ICD-10 code, which is a code from International Classification of Diseases standard, and the amount for the claim. Let's take a look at a graph data for a healthcare and pharma industry example next. Uncovering referral relationships is a lot easier in a graph database, as the patient, prescriber, and claims data is pre-connected in the graph database. Consider the example where Dr. Douglas Thomas, a general practitioner, sees a patient in San Jose, P1003, on September 8, 2017, for shortness of breath symptoms resulting in the claim C10005. The same patient, P1003, sees Dr. Helen Su, an interventional cardiologist, on September 20th for an angiography, and again on September 23rd for the actual operation. TigerGraph visually shows all these claims connected with the patient and the prescribers in the Graph Studio, so that the data analyst can understand the relationships intuitively. This is a 4-hop or 4-level connection from Dr. Douglas Thomas to Dr. Helen Su, with the common patient P1003 connected via 2 claims, one for each prescriber or doctor. The graph database also links them based on a time window to deduce referral relationships. In this example, the claims occurring within 4 weeks are considered for establishing a referral relationship. It takes 4 hops or steps from traversing from the referring physician, Dr. Douglas Thomas, to the referred physician, Dr. Helen Su, via relevant claims, identifying 3 common patients, P1003, P1004, and P1005, over the month of August and September. A referral edge or relationship is established between Dr. Douglas Thomas and Dr. Helen Su, and the relationship edge carries important information such as the number of patients referred, healthcare condition groups related to the referred patients. The prescriber data can be added in to provide specific drugs for cardiac care that are frequently prescribed by both physicians. Armed with these insights, pharmaceutical companies producing the cardiac care medication and the medical equipment manufacturers producing stents and other products for the cardiac surgery can market these products to Dr. Douglas Thomas and the referring network, including Dr. Helen Su, for the San Jose healthcare market. Healthcare providers can identify referral networks with prescribers, benchmark cost of care for specific conditions such as cardiac care, and finding the outliers. This includes good or efficient referral networks that provide the same level of care and outcomes, while controlling overall cost of care, and potential networks with unusually high cost of care, indicating potential fraud or abuse. This example we looked at for healthcare and pharma to uncover referral networks is a classic deployment of a graph database and analytics. Graph is widely used every day in all industries, so let's look at how we're using graph databases and analytics every day next. You use graph databases every day and probably do not realize it. Let's take social media for example. Facebook, Twitter, and Instagram all use graph databases and analytics to understand how users relate to one another and connect them with the right content. Every time you do a Google search, you're tapping into Google's knowledge graph. Amazon product recommendation is also powered by graph analytics queries. Wish.com is another popular e-commerce website that has grown to billions in annual revenue in just 4 years since 2015. Wish utilizes a graph database for highly targeted or personalized product recommendations to fuel their growth. Zillow is a popular website in the United States for buying, selling, and renting homes as well as apartments, and they utilize graph database and analytics in a variety of ways. Let's dig deeper into these examples to understand the daily usage of graph database and analytics. Let's take a look into a website most of us use every week, LinkedIn. As we look up someone on LinkedIn, for example, TigerGraph's Vice President of Marketing, Gaurav Deshpande, we are interested in finding answers for specific questions about a possible relationship between you and Gaurav. How are we connected on LinkedIn? Do we have common professional contacts, or are we connected via school friends? Do we have common groups such as big data, analytics, Hadoop users, or a graph database related to a group on LinkedIn? Every time you use LinkedIn and see first, second, or third degree connections, you are getting results from the site's professional network graph built on a graph database. The second represents degrees of separation between you and someone else on LinkedIn's professional graph. This is a database query that figures out how many degrees or hops we are separated by. The second degree means that one person knows someone that in turn knows you. When you type TigerGraph into a Google search bar, you'll see all of these search results. These web pages are ranked by Google using an algorithm called PageRank. PageRank is a graph analytics algorithm. So every time you search on Google, you're using graph analytics. You would sometimes get emails from Zillow, as well as recommendations on the site under homes you might like or homes you will love. This comes from a similarity search based on your browsing, search, and what's part of the saved homes on Zillow. Every time you use Zillow, you're using TigerGraph's multi-dimensional entity and pattern matching. The dimensions in case of a house are basic features such as location, square footage, and parking, to more advanced dimensions such as availability of a pool, walking index indicating how easy it is to walk to the basic necessities such as groceries and view from the house, if any. This is based on similarity search or pattern matching to find similar customers, combine their browsing, search and save home patterns with the customers in question to zero in on best recommendations for a specific customer. Let's take a look at another use case where a graph database is being applied by Visa Corporation to understand and manage the impact of outages of a specific resource such as storage or computational servers on the business. This use case is called Network and IT Resource Optimization through Impact Analysis. We have covered this in Graph Gurus episode 9, an educational webinar series for data scientists, developers, and architects, and you can register and replay all of the Graph Gurus webinars, including this episode 9, where this is the use case covered in depth. Let's review the schema for a moment. At the bottom right hand of the schema, you can see the storage array vertex. One storage array may have multiple pools as a part of its logical structure. Each pool, in turn, may have multiple LUNs, or logical unit numbers. LUNs are assigned to host server, connecting storage with computing. To the left of the host server, you have applications that are running on the server. And there's an edge called app call, which models the relationship of applications calling other applications as part of the processing. This models the dependency among applications explicitly. Each service leverages one or more applications and is managed by a leader or a manager who is responsible for managing the service. An application may have one or more warnings of different types. Let's compare the labeled property graph on the left-hand side of the chart with the same data represented as an RDF graph on the right-hand side of the chart. Property graphs support attributes on vertex or data objects as well as the edge. Left-hand side shows 3 attributes for a claim vertex. On the right-hand side, each node is represented by a unique resource identifier or URI and cannot carry any attributes. The RDF structure comprises of a subject, such as a claim, an object, such as the patient, and predicate, which models the relationship between subject and the object, in this case the claim and the patient. Each attribute, Rx fill date, ICD-10 code, and amount must be modeled as a separate node in the RDF graph and must be connected with a unique predicate such as has date, has code, and has amount, as shown in the RDF graph. RDF graphs came about as a part of a semantic web movement and are outstanding for publishing public datasets that are shared openly due to their easy-to-understand 3-part structure. They are, however, very verbose and have several times the number of nodes or vertices compared to the labeled property graphs. There are a few other differences, including the graph query language for either type of graph, which are all summarized on the next slide's chart. Please note that labeled property graphs and RDF graphs are very complementary and are used for different types of use cases and datasets. RDF graphs are used for datasets that are shared widely or publicly, such as knowledge repositories that are relatively static or where the data isn't updated very frequently. Labeled property graphs are meant for static as well as dynamic or frequently updated datasets. In fact, knowledge graphs or repositories are often loaded into a graph database to analyze and serve up real-time insights based on deep link analysis of data. Please replay Graph Guru's Episode 1, TigerGraph's webinar series, which shows a good example of this in context of an enterprise knowledge graph. Another key difference between the two types of graph is the graph query language. Currently, there is no standard graph language for property graphs. Popular languages for property graphs include Gremlin and GSQL, both of which are Turing complete, and Cypher or OpenCypher, which isn't Turing complete. There is a working group made up of multiple graph database vendors, including Neo4j, TigerGraph, working on a new standard for the graph query language for property graphs called GQL. RDF graphs, on the other hand, have a standard query language called Sparkle. Now that we've gone over all the slides, let's do a quick recap of what we learned. So we learned that a graph is a collection of vertices and edges connecting the vertices. Graphs model data in an intuitive manner. We use graph databases every day to answer questions about relationships. Graphs are used in multiple industries including healthcare, pharmaceutical, financial services, government, telecom, IT, and e-commerce. And RDF and labeled property graphs are used for different types of datasets and use cases. These are the key questions which you have to keep in mind when answering the quiz online. Which of the following sites leverage graph databases? Why are graph databases ideal for modeling and analyzing relationships? Can graph databases be used for analyzing data related to machines or hardware? Which of the following are not typical use cases for graph databases? Is there an established standard for query language for labeled property graphs? Is there an established standard for query language for RDF graphs? Please indicate if the statement is true or false. Each attribute must be modeled as a separate object or node in an RDF graph, as the nodes do not have properties or attributes. And finally, please indicate if this following statement is true or false. RDF graphs are suitable for deep analysis of relationships.